So here's a first sketch of a gradient ascent method, and it works as follows. So our goal is to maximize this function L of v, where the derivatives take the following form. And what I've actually done here is used usual vector calculus definition of derivatives. So I have dLv by dv is now going to be a vector whose first component is the derivative with respect to the first parameter, and whose second component is the derivative with respect to the second parameter. And these are derived in the way I showed you on the previous slide. So this thing is a m-dimensional vector itself, basically giving the gradient. And this is easily calculated using the definitions I just showed you. And so the most naive gradient-based method would perform as follows. We would initialize v to be the vector of all zeros. At each point we would calculate the gradient, call this capital delta, and then we'd basically do this search I was talking about before. Okay, so we would start at some point, we'd calculate the gradient, we'd do a line search to find the optimal distance to move, and we would move to that point. So beta star is basically how far we have to move, and so we're calculating the optimal value for the function if we just move in this one direction. So beta is the distance we move in the direction capital delta, and then we reset v to be this new value here, and we iterate until convergence. So again, we calculate the steepness and the steepest line of ascent, i.e. the gradient, and we move the optimal distance in that direction, and so on until we basically have reached some optimal value, or some value that we think is optimal. The good news is that you, in general, will not have to implement these kind of gradient ascent methods. They've been developed for years, actually decades, and quite sophisticated methods have been derived which in practice work extremely well. So one thing to note is that the vanilla gradient ascent method I just showed you can be rather slow. It can tend to sort of get stuck in these long valleys and take quite a few iterations. So more sophisticated methods are used if you're interested in looking it up. Conjugate gradient methods. One very commonly used method for these log linear models is an algorithm called LBFGS. The good news is that many implementations of this algorithm or other conjugate gradient style algorithms are available. And they in general assume a rather simple interface. Okay, so they're basically going to assume that given a parameter vector v, you will calculate the value for LV and you'll calculate the gradient. Okay, so this is the objective value. It's one thing you can calculate. This is the gradient. And with these software packages, they will then optimize the function. And what they'll basically do is start at some initial point, for example, all zeros, and they'll move in some direction which takes into account both the gradient and also the previous directions that the algorithm has moved in. And these can be very, very efficient in optimizing the function L of v. And that's about it. So if you can implement functions L of v and dl by dv, this gradient function, given one of these existing packages, you can optimize L of v quite efficiently and find these maximum likelihood estimates.